Hi everyone, welcome to the next video. We're still talking about integration. This particular video will be about finding the area between curves. We found the area under the curve, between the curve and the x-axis, and now we're going to be extending that concept. So this video is going to have a lot to look at, not as much to write down. I mean, you can sketch some of these diagrams very simply, but this illustrates very clearly what we're up against. We would like to find this area between the top curve and the bottom curve, between the x-coordinates of A and B. So we want this area of a region. So it kind of intuitively makes sense that if we keep the same region and we find the area under the top curve, between the area of the top curve and the x-axis, and we subtract from it the area of the bottom curve, that we're going to end up with that part underneath. And so this is the notation behind that. The area of the region will be the area of the top curve minus the integral of the area of the bottom curve, or finding the area of the bottom curve using the integral. So in calculus language, there's a lot of notation that has to do with this. And basically integration, as you recall, is the sum of all the areas. You know, we divide up this region under or between the two curves into rectangles of the same width, delta x. And we find the area of each one of these rectangles, and that will approximate the area under the curve. That's what we're doing when we find the integral. The fundamental theorem of calculus says we can use the definite integral to find the same value as we would if we use left, right, midpoint, Riemann sums. Okay, so that's what this means here. We have delta area, right, the change in area, height times width. And so we have the function minus the bottom, that's the height of the rectangle, times the width, which is delta x. Take the limit of that as n approaches infinity, n is the number of rectangles, right? Then we get the area is equal to the limit, and that becomes, by fundamental theorem of calculus, that becomes the definite integral. So basically what we're doing here is we've spent a lot of time finding the integral, setting up integrals, finding the definite integral using the fundamental theorem of calculus. And now what we're doing is we're adding stuff to the beginning. So we're actually adding the application part of it. And so here is finding the area of the region bounded by the graphs given here. You know, you've got the top graph and then the x-axis, which is this right here, g of x equals 0. So graphing it, we can see that this forms a parabola, an upside-down parabola, negative x squared, right? And it is going to have, it's going to intersect the x-axis at the zeros of this function. So we're once again relying on our algebra to be able to solve this. You can see a representative rectangle under there. But what we're going to do is we're going to set up the integral, right, because we want to find this area, and we want to go from a to b, and so those are the x, so this is going to go from negative 3 to 1 of the top function, which is f of x, minus the bottom function, which is g of x with respect to x. And so if I were writing this out, this would be negative 3, 1, this would be 3 minus 2x minus x squared minus 0 d of x. And then I could either find that by hand, or I could put that in my calculator if that's, you know, allowed on that part, to find an actual answer, and that answer would be the area of the shaded region. Now, sometimes you can't integrate analytically, right? Because there's no way to integrate the natural log of x. So that would, or at least by hand. So you would have to put that into a calculator and to find the definite integral. But once again, it's the region between 1 and 5 of this function, y equals x, minus this function, which is the natural log of y. X, sorry. So once again, we did several of these problems in class. So this is not really a detail video, it's more of a concept video. I just want you to kind of get the idea of it. You know, the ones we did in class, we actually had the graph. It was already graphed. Then we learned to graph. We did some graphing by hand. And these are some of the situations in this video that you'll run across as you're graphing them. And so I want to talk more specifically. So here's just another example of finding the area of the region bounded by these graphs. So this is what you're given, right? So you would have to be able to graph this upside down parabola. Plotting points would be a good way to do it. You could put a 1 in and a 6, right? Or a 5, however far, 2 to 4, whatever, so that you could get where these are. So I would know between 2 and 4. So if I'm writing this out, I want between 2 and 4. I can see here that it's this function that is the top. So I would be doing 16 minus 1/4 x squared minus then this bottom function, which is 12 minus 1/2 x, and then dx. And now you could distribute the negative, make it all into 1. If you had to do it by hand, that's what I would do. But if you're just going to put it in a calculator, you can just type it in that way. But don't forget then to put this second function in parentheses and distribute the negative, or you're going to get it incorrect. It's going to be incorrect, okay? Okay, so this one, you've seen this diagram before, but what I wanted to point out to you was that this is the area of a region between intersecting curves, okay? We just said that the curve was g of x equals 0, right? Another way to say that would be y equals 0 or the x-axis. So this was typical, but what we found was we needed those 2 points right here to be able to set up our definite integral. So if we don't have those points, or those points aren't easily obtainable, then we're actually going to have to use either algebraic methods, or we're going to have to find the intersection between those 2 points to find these 2 values right here. So, and that's what the next ones are going to be about. So sometimes you have a situation where, if you look at this is an odd function. It is symmetrical about the origin. And you can see that the area on the right is above, which is a positive area, and then the area on the other is below, right? And so these 2 areas they look exactly the same, but one is above, one is below. They cancel each other out. Another interesting thing, and probably more significant, is that on the right side, this function is the one that's above and this one below. But on the other side of the y-axis, they switch. So in order to process this, you would have to do this one of 2 ways. If you know that the area on either side is the same, then you can pick this side. And I would say from 0 to 1 of the top minus the bottom, dx. But I know that this is half, so if I multiply that through by 2, I'll get the whole area. Or you have to write them separately, and so you would do negative 1 to 0 of x minus the cube root of x dx plus the area from 0 to 1 of the other one, what I just had up here, the cube root of x minus x dx. And so you'd have to do 2 separate areas to be able to get that to be correct. Now, this brings up another point. What if you get them upside down? Like, what if, for instance, on this one, you write it backwards, and you know it's backwards because you end up with a negative area. All right? If that happens, you know you can't get a negative area. The result of this is always going to be a positive area, always. Area will be positive in this instance because we're trying to find an actual area, kind of like, time can't be negative. It has to be positive. Distance has to be positive because you don't have a negative distance. Negative just means opposite direction. Well, this one, you're going to have a positive area. So don't just put, like if you get it backwards and you get an answer, don't just change it to positive and call it good. Go back and take the absolute value of your area, and then as you're doing it, because otherwise you will get an incorrect answer. So here's another picture, same kind of thing. You can see that the functions change positions. Function changes positions, and top minus the bottom, just like that. And so once again, you notice that the areas are the same on either side, but you're going to have to either set up 2 or you're going to have to double it. Now, here is another interesting graph, and there's a very important concept associated with this graph. You can see here that I have 2 functions. I have x equals 1/2 y squared minus 3, this one, the red, right? And as you can see, this is not a function. It is a parabola. It's a right-facing parabola, but it doesn't pass the vertical line test, and so it is not a function. And then I just have this line, y equals x minus 1. So I have one that's solved in terms of x, and I have one that's solved in terms of y. And if I sit here and think, if I go across the whole thing, I can see here that in this part right here, it's very obvious to see that red is above blue until it gets to about here. And then right here, you can see that blue doesn't even figure into it. I have red over red. So how am I going to set up this area vertically, right, in terms of x? So let me show you what that looks like, because you can do it. Okay, so here, this is what you've got. You have the top part, right, this red right here, is solved, that same equation is solved in terms of y. So here's the top part, right, because it'll be plus or minus the square root. And then here's the bottom part, the negative. So you got the green and you've got the red. All right, so I've got actually now 3 functions that I would have to set up. All right, so you see this yellow part right here. This would be a traditional part. I would need to know where this is. It looks like it's at -1. So I would have the integral from that would be from -1 to about, what is that, 5? And then that would be the square root of 2x plus 6 minus the blue, which is x minus 1 dx, right? So that would be the yellow. And then over here, this part right here, right, I would have to set up, it looks like to me, I would have to set up 2 more regions, right? I would have to do this one where I have, actually, I guess just one, because I would have red over green here. So from -3 to -1, I would have to set up something totally different, minus this dx, right? So I could do just this and double it. I mean, there's different ways of setting it up, but you can see that it's getting very complicated. So let's see if we can think of a different way that might make this a lot easier. Here is the same graph, same green region. You can see it here. Only this time, if you'll turn your head, let's think about this in terms of y. So I would have this intersection point here and this intersection point here. And if you turn your head, you could see that this would be the top, right? And this would be the bottom if you turn it, which, I mean, I think I could probably turn it. I don't know. But if you turn, oh yeah, looky here. There we go. So do you see that now this is going to be the top, the blue will be the top, and the red will be the bottom, and I would go from -2 to 4. Only, let me put it back, only it's on the y. So what you would need to do is you would need to solve each of these equations for y, not x, but y, right? Just like they are here. So x equals something in terms of y, right? Something is in terms of y, so you're solving it in terms of y. Only this time I'm going to be setting up the integral in terms of y. So I would have from -2 to 4 of, instead of top, it's going to be right, and this is going to be left. because I'm doing this in terms of y. So I would do the right function minus the left function, dy, not dx, dy. And then these are y values. And then integrate the same. It's still going to equal the area of the green region. Area of green. There we go. So this part, you need absolutely this part in your notes. And at this point, I think you should also have some diagrams in your notes. Maybe you don't work the problem all the way to an answer, but you at least have a picture, a diagram that you could go back to and look at. So when you have something that you have to divide up into 3 regions, if you do it through the x, then you might just turn your head sideways and see if you could set it up much more easily in terms of y. And so here on this screen here's the theorem at the top, here's the definition, the area of the region between 2 curves, gives it written out in notation. And then here at the bottom, what I really, really like is if you have vertical rectangles, so your rectangles go up and down in terms of x, right? Or horizontal rectangles, which go in terms of y. So this screen is hugely important, and I'm going to be looking for this one in your notes, along with some diagrams, and not necessarily the worked out solutions, because I really feel like you could do that on your own. But those diagrams need to be in there because you're going to come across those, and those will be the hardest things to find. So the very last example, and I put this in here more for a methodology rather than an actual answer, but it says choose the area of the region in the first quadrant bounded by the graphs of y equals x to the third and y equals 2x minus x squared, and then it gives you a bunch of answers here. All right, so we need a methodology. So the first thing we need to do is, however we need to do it, we need to graph the 2 functions. Okay, then we need to find the boundaries. We need to find, find A and B, right? So we need to know, it says first quadrant, so probably A will be here, and then wherever it crosses, if there's some way of crossing, maybe it crosses here or here. I don't know what those look like, but this says one looks like it's some kind of cubic function, and the other is an upside down, right? So it's probably going to look something like that. So you're going to need to find A and B to set up the integral. You're going to need to set up the integral. Once you figure out which is top and which is bottom, and then solve. Now, when you solve, you can solve either analytically, or with the calculator, and you need to know how to do both. Calculator. Another thing, if it's a calculator problem, you could graph the 2 functions on your calculator. Put one in y1, one in y2. You could use that also to find A and B if they're intersecting. So you need to have those calculator skills to be able to quickly put a couple of functions into your calculator and find out what situation you have. All right, so I hope you took good notes. There's a lot of great concepts in here. I think they'll really help you as you're working on these problems and these types of problems with integration as an accumulation function and the area between curves. So I will see you in class.